All right, we're going to finish off Chapter 4 with a section entitled Trapezoidal Rule. And the Trapezoidal Rule is similar to LRAM, RRAM, and MRAM, except that instead of using rectangles, it uses trapezoids. And the formula is a little weird at first. It has area, and again, it's an approximation. It says width in quotes. You can almost think of width as being height if you want as well, because the trapezoids are turned on their sides. And then it has this strange, very long parentheses with yo and yin at the end, and those both have coefficients of 1, and everything else in the middle has a coefficient of 2 on it, so it's kind of weird. Don't worry about memorizing this formula. I think you're going to memorize it without meaning to when you start to see some examples, which we're going to do right now. I want to estimate the area of Lake Erie. Lake Erie is not a function. You know, the glaciers, when they receded, they weren't like, let's make sure this is a function. In fact, it fails the vertical line test. At Sandusky, you can see that that's no good. In fact, the whole lake fails the vertical line test because all those vertical lines hit Canada and the U.S. shoreline, simultaneously there. So it's not a function. So how do you find its area? Because you can look up the surface area of any lake on Google, and it'll tell you what the area of Lake Erie is. So I'm kind of wondering how you do it. Before man was in space and we were able to have images of the Earth, we kind of had to figure things out differently. So what they did is they took a couple lackeys in a rowboat and sent them across Lake Erie with a tachometer so they could measure distance. And they sent them out near Michigan, and they went across to the shores of Michigan, and they're like, all right, that was 17 miles. And then they did the same thing near Port Clinton and got 31 miles, then 46, 59, and so forth, all the way to Buffalo, which is just 9 miles across. Trapezoidal rule only works if you have edges that are straight on the left and right-hand side. So we're going to ignore the little portion of the lake by Michigan. And I have a feeling if you get into the city of Buffalo, the shoreline's not straight north and south. So anything that's, kind of curly over there, we're going to ignore that too. And we're going to connect everything else with, you guessed it, trapezoids. There's a trapezoid by Toledo. Here's another trapezoid by Sandusky. The west suburbs of Cleveland. Downtown as well, out by Ashtabula, and so forth and so on, all the way out to Buffalo. As you can see, when I'm making these trapezoids, I'm losing a little bit of accuracy. There are places where I'm missing a little bit of the lake. I'm counting Marblehead and Lakeside and Port Clinton as part of the lake when they're really not. So this is not perfect. I'm missing Sandusky Bay, but it's really, really close. And just like the Riemann rectangles, the more trapezoids you have and the skinnier the trapezoids are, the less error you have because you don't leave off that much of the lake up by Canada there. It's a better approximation. If you can make these trapezoids super skinny, you'd have a perfect answer. And that's how you figure out areas of things where you can't integrate and you can't have a function to go off of. All right, so I'm going to go ahead and start by taking the area of a trapezoid, which hopefully you remember from geometry. And the area of a trapezoid is 1/2 height, base 1 plus base 2. If you can't remember that formula, just consider this. A trapezoid, let's say this trapezoid, a height of 4, this top base is 3, the bottom base is 7. You could have that. And then think about this. You have a triangle, but the top base of the triangle is 0. The triangle follows the same formula. We know the formula for triangle is 1/2 base times height, but a triangle doesn't have 2 bases. The trapezoid is simply a triangle with another base. What do you do with the extra base? Just add it. Okay. So hopefully that can help you remember the formula. All right, let's start out by taking the first trapezoid, the one over by Toledo. Its area is going to be 1/2 height, but the height is defined to be the distance between the bases. And the bases are the two sides of the trapezoid that are parallel. So really these trapezoids have all been turned on their sides. Notice it says that we're going across the lake every 20 miles. That means that this height is going to be 20. In fact, the height of every single trapezoid in my picture is 20, so that you're going to have 1/2 and 20 every single time. The two bases on this Toledo trapezoid out here are going to be the 17 over by the state of Michigan and the 31. All right, so that's the trapezoid by Toledo. Now we're going to move to the next trapezoid. I'll call it the Sandusky trapezoid. Well, if you add that trapezoid onto the area of the lake, it's going to be 1/2. Again, the height is 20. It always is. And this time you're going to use, well, you're going to use a 31 again. Even though you used it in the Toledo one, it also gets to be used in the Sandusky trapezoid. And then the 46. And then you would do it again. And don't worry, I'm not going to travel all the way to Buffalo. Oh, that'd be horrible. But can you see that every single one of these has a 1/2 times 20 in front? So rather than writing that every single time, can't we just write it once? We'll just sort of factor it out. Isn't that just a 10? It's just like 20 over 2. And sure enough, if you go back and look at the formula, that's exactly what you see. It's the width, in this case 20, divided by 2. You can see why I said that some people call it height instead. And then also, you may have remembered that there's a 1 in front of the first term. Everything in the middle has 2's. I don't know how many there are, but they all have 2's. And you get to the end, and there's a 1 again. And that's because this first one, which I believe was a 17, and this last one over by Buffalo, New York, was a 9. Those are only going to get to be used in 1 trapezoid each. But everything else in the middle is going to be used in 2 trapezoids. That's why you see all these 2's on them. They're going to get double use. So because of that, I think you can see that, oh man, this problem not only is a lot easier than it's sounding, but I can do the whole thing on my calculator. And you're right, you totally can. That's why people tend to like trapezoidal rule. So our area is just going to be 1/2 times the 20, or 20 over 2 if you prefer. This 17 is going to get used once. Everything else in the middle is going to get doubled. And then plus 9. The 9 is only going to get used once. If you put that into your calculator, you'll get the approximate area of Lake Erie, which will be 10,540 square miles. Okay, you're going to see problems like this in textbooks. I have a couple on my worksheet that I give you tonight, just because sometimes they like to use regular, functions. So 1/2 x squared plus 1, that graphs as a parabola. That's an upward opening parabola. I'm going to make a quick sketch of it. I can tell that it goes through the point 0, 1, -4, 9. It's going to come down and then kind of bend back up like this. This is not by any means a perfect drawing. I don't pretend that I can do that, but I'll label these points. Okay, first things first. N equals 4. N is the number of trapezoids that we want you to use. You already heard me say that the more trapezoids that we used on Lake Erie, the more accurate we would be. Here's the problem with homeworks. Some people will use 4 trapezoids. Other people are overachievers and they'll use 8 or maybe 16 trapezoids. Other people are going to use 2. So we have to come to an agreement, otherwise we're all going to get different answers. So usually N equals 4 is a pretty nice compromise. That's usually what College Board will use. They'll use either somewhere between 3 and 5 on most years' tests when they test trapezoidal. So I knew that since I was integrating between -4 and 12, that was a total distance of 16 spaces. And since I have 4 trapezoids, 16 divided by 4, each trapezoid is going to be 4 units wide. That's why I counted by 4s on my graph. If I connect this with straight lines to make my trapezoids, you can see that these are my trapezoids. Here's my first one. I can color that in. Here's my next trapezoid. Next, make that polka dotted. And the last one I'll just leave plain. All right, we're going to add those 4 areas together. Here we go. The area is approximately, because remember, this is a trapezoidal approximation. All right, 1/2. Each of the trapezoids has a width of 4, or a height of 4, if you want to think of it as height. The first base, this +9 right here, is only going to get used once. Everything in the middle is going to get doubled. And the last one, this 73 right here, is only going to get used once. Okay, so there's my setup. Let's see what we have. 1/2 of 4, of course, is 2. We have 9. Plus the stuff in the middle, all this good stuff, that's going to be 86. Plus the 73 on the end. That's going to work out to 2 times 168, which will be 336. 336 is the area. Interestingly enough, if you were to actually figure out the exact area by integrating, it would come out to be 314 2/3. And of course, people are going to ask me, why on earth are you going to want to use trapezoidal rule when you can get an exact answer just integrating? And that's a great question. You wouldn't. And so you're going to see textbooks, just because they're trying to get you to practice with trapezoidal rule, they're going to give you problems like this and be like, hey, get a slightly inaccurate answer. The reason that trapezoidal rule exists is for things that don't have equations, that can't be made into functions. Let's say that you were in charge of a marketing firm that was doing some work for a major American sports team. And they wanted to give their fans, decals that they could stitch onto their shirts or whatever. And so the promo was, hey, let's give the first 20,000 fans one of these decals. And they're like, oh, cool. Well, how big's the decal? Well, obviously this Arizona Cardinals logo is not a function. It fails the vertical line test. Even the feathers in the back kind of fail the vertical line test on the bird's head there. So what we need to do is use trapezoidal rule. So we're going to connect. I just put a dot at the end of the bird's beak and called it 0, which is cool. As you can see, this is not perfect, but it's close. And we'll just add up all the trapezoids. So the area, the Cardinals logo, is going to be 1/2 height, which in this case is 4 inches apart. And then we're going to multiply that by, the zeros on the end only get written once. I'm going to write them anyway. And since I'm running out of room, I'm going to come down here. Everything in the middle is going to get doubled, plus the 0 at the other end. All right, putting this all together, you get a 2 out in front. The entire bracket is going to turn out to be 250, which means that this cardinal logo, each one, has an area of 500 square inches. And really, I should say approximately 500. It is an approximation. It's an estimate. All right, cool. I want you to take a moment, pause the video, and see if you can figure out the area of this Red Wings logo, and we'll see how close you are. Don't forget to put your units on your answer. So go ahead and pause me and see what you get. All right, I got 345, kind of a cool answer, square centimeters. And there's my work to go with it. On a test or quiz, you always want to show your work, because if all you have is an answer and it's wrong, I won't have any idea if you know what you're doing or not, and I can't give you partial credit. So anything I type into the calculator, I just write out to give my evidence that I knew what I was doing. That way, if you just miss one number, I'll easily see what it is. So, anyways, 345 is correct.
Okay, our last 2 problems are going to be free response style questions. Number 5 says the temperature of a cup of coffee is modeled by a function c. It's differentiable, which tells me it's also continuous, between 0 and 10 minutes, And C is the temperature of the coffee in degrees Fahrenheit. Selected values are in the table. We want two things. Using correct units, explain the meaning of that thing, 1/10 integral C of t dt. And then estimate it using the trapezoidal rule, trapezoidal sum. Okay, first things first, explain the meaning of it. That's sort of easy. When I look at that, and especially when I see the 1/10 in front, that's screaming out average value to me. And sure enough, that is going to be the average value or average temperature of the coffee in degrees Fahrenheit between 0 and 10 minutes. So I just have to write that out. Okay, so that red portion is finished. And now we have to figure out, well, what is the average temperature of the coffee? Estimate it using a trapezoidal sum. Okay, so we're going to break out trapezoidal rule. We'll do that in blue. All right, the trapezoidal sum, we know that the area of a trapezoid is 1/2 height, base 1 plus base 2. We're going to have 4 of these trapezoids. Let's see, the first interval is just from 0 to 1, that's 1. And we're going to take the 211 plus the 188. Okay, 1/2 height, base 1 plus base 2. The next height is going to be 3, because we're going to go from 1 to 4. And that's going to be the 188 and the 116 added together. 2 more. 1/2 height. The next height is 4, because it's 4 to 8. We're adding 116 and 93. Finally, I think we can fit this in. 1/2 height. The height here is back down to 2. And it's 93 plus 82. The whole thing is multiplied by 1/10 out in the beginning. The 1/10 will drop down. Feel free to pause the video if you want, but I went ahead and figured out the brackets. Okay, in case people are back, it's 1,248.5. 1248.5. Obviously, the 1/10 is still out there, so we have to move the decimal point over one place, and that's going to give us 124.85. If you'd like to put an extra 0 at the end and make College Board, happy with the 3 places, that's fine. But since this is perfectly 124.85, you don't need to. I am going to put the degrees Fahrenheit on there just so the judges are happy with me. Better safe than sorry. It didn't say to have it because the other part had correct units already, but I'm going to be safe. And that is the answer. So part 5, full credit for both. All right, one more free response style question, number 6, and then we'll call it a day. Number 6. A train runs back and forth on an east-west section of track. You may recognize my motivation here being a recent College Board question. The train's velocity is given in the table, selected values. And when time is 3 hours, train A's position is 240 miles west of Tulsa, Oklahoma, and the train is moving to the west. So we're moving away from Tulsa. Write an expression involving an integral that gives the position of the train in miles from Tulsa at time t equals 9. Then use the trapezoidal rule, find a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train in relation to Tulsa at time t equals 9. So again, we want 2 things. We want an expression to be written, and then probably we'll take that expression, use some trapezoidal on it, and get an answer. That little dot you see is Tulsa, Oklahoma. All right, we get the tracks running through Tulsa. Let's make Tulsa a little bigger. Okay, train A starts out right here, 240 miles to the west. And train A begins moving to the west. And that would make sense at time t equals 3 because you can see that the velocity at 3 is negative. And the 2 negative graph positions on a map would be west and south. And so, this train's heading west as the directions say. All right, so let's do this. The position will be negative 240. That is the 240 miles west of Tulsa that we're starting with. And then we want to see how far the train has moved, and that, my friends, is an integral. We're going to integrate from 3 to 9 of the velocity formula with respect to time, dt. That'll be how far east or west the train has, changed its position. And we'll add that to the negative 240 and we'll see where we're at. The problem is, I said the velocity formula, there isn't one. Looking around, there's no velocity equals anywhere. And that's why they told us to use a trapezoidal sum. So first off, we have the first part done. It says write an equation using an integral for the position of the train from Tulsa. We did that. And then the trapezoidal sum will help us figure out what this integral of velocity ends up being. Okay, so the final answer will be negative 240 plus what we get from the trapezoidal rule. All right, since we're only going to go from 3 to 9, we don't need the 0, 10 in. That's just there to maybe be tricky, I suppose. So let's start off with the 1/2 height, base 1 plus base 2. We'll go trapezoid by trapezoid. 1/2 height. Here the height is 3 because we're going from 3 to 6. That's a difference of 3. And it's going to be negative 57 and negative 43. That adds up to negative 100. I'll just save us a step here. The second trapezoid is 1/2 height. The height here is only going to be 1. You're going from 6 to 7. And that's going to be negative 43 plus 64. That ends up being 21. And then finally, we have one more to go. 1/2, 7 to 9. That's 2. And 64 plus 78. That's going to be 142. The position, I'll call it X since we're just running east and west along the X-axis. The position at 9 is equal to all this added up. Let's see, we've got negative 240. This is going to be negative 150. This will be 10.5. That's positive. We're coming back east. 1/2 and 2 will cancel, so this is positive 142. Adding that all up makes negative 237.5. So making a statement, I'll say at time t equals 9 hours, the train is 237.5 miles west of Tulsa. And that, my friends, is how you use the trapezoidal rule in calculus. Great job. That concludes Unit 4. Hopefully you'll come back and join me for the beginning of Unit 5 as we meet next time. See you then.